Time's 11 o'clock, so let's begin here. So assignment number 2, hopefully all of you got my listserv posting from yesterday. That is available on the website. We will talk about assignment number 2 at the end of class, and right now it's due Friday, February 20th at noon. We will continue in the bootstrap section today. Are there any questions before we get going? Okay, we left off last time on page 24. So we were talking about this AC data, which basically represents 12 failure times of air conditioning equipment in an airplane. And what we're interested in doing with this data set is to estimate essentially the mean failure time for this air conditioning equipment. And so what we did previously was we took some resamples using the sample function in R, and also did some calculations. And we also did the basic bootstrap confidence interval with it to estimate then the population mean. Now very often you can do some of these calculations more easily using what's called a boot function in the boot package. I briefly mentioned this package before. This is a package of a whole bunch of R functions that make your lives easier with respect to the bootstrap. It was written originally in S+, for the Davison and Hinckley textbook. It has obviously then since been converted to an R format. Now note that if you ever do want to look at the Davison and Hinckley book, Chapter 11 of that book goes into detail about how to use the boot package. Also, with chapters 2 through 10, in terms of the exercises, there are exercises that give you code that allow you to get some experience with using the boot package. So that's one of the nice things about Davison and Hinckley's book, and actually, while nowadays that's very common to do that, to have, let's say, R, or in that case, S+ embedded inside the book, that was actually one of the first first books that actually did something like that. So you can see how we've evolved. Where in the past, like when I was a student, basically, and maybe I've told you this before, if you wanted to know how to do some of this stuff using statistical software, you had to just go figure it out yourself. There weren't books on it. You know, your professor might write some SAS code on the board, and you copy it down and you run it after class. That's the extent to it, where it came from. But at least nowadays, in terms of textbooks, at least the way that I teach, I want to make sure that you actually know how to do this stuff.
Quick question.
Yeah.
In the CDF, do we normally always use the exponential function to test?
Well, we use the exponential function with this example because it was failure data, and that's the easiest distribution that's used for failure data.
But depending on what the data is, will it change?
Yeah.
Okay.
Oh yeah. Well, I mean, just because we're using the bootstrap here doesn't mean every EDF is going to look like a CDF from an exponential. No. Okay. It was just failure time data. You know, if you take STAT, it's 872, the survival analysis course. 876. The first distribution you often look at is exponential.
So is it like plot the EDF first and see how the shape is, or?
I just did that because in the example in the book, that was a particular distribution that they proposed to use.
Right. Yeah.
And as you might expect, the gamma distribution even fits better. And what this is going to lead up to is eventually, well, I haven't written up the notes yet for that, and we're going to talk about the parametric bootstrap. And so if the exponential seems like a decent fit to the data, then what we're going to do, instead of taking take resamples from our 12 observations, instead we will take samples from an exponential distribution. Okay? So stay tuned for that. Okay, so if I want to use then the boot package, I have to say library boot. Now this package is automatically installed in R when you install R itself. But in order to use the package, you do need to say, let's see here, there we go. You do need to say, where is it? There we go. you do need to say library boot. And I guess just to give you a little bit more background, so packages in S+ are actually called libraries. And so now you have an idea of why the word library is used instead of package when you are saying, hey R, I want to use this package. Okay, now the boot function itself, I'm going to actually skip down a little bit. This will be on page 25. Now, since we are taking resamples from my original data, I want to, of course, set a seed so I can reproduce my results. So you always will want to set seeds whenever you take resamples. So I set my seed there. And then to use the boot function, which is the one that primarily does your calculations for you, or a large number of your calculations for you, here are the arguments. Data equal y. Remember, my data is in a vector y. The statistic that I'm going to calculate for every resample, you have to actually write a function to calculate this statistic. And this function has to be written in a particular format, which we will talk about in about 1 minute or less. And so I say statistic equal, and I could have used a different name for my function. I just decided to call it calc.t because it makes sense. I'm calculating my statistic t. I will often use the letter t for our statistic of interest. We're going to use 4,999 resamples, so that's the R argument. Sim stands for how are you doing your Monte Carlo simulation. Remember Bootstrap, you're basically doing Monte Carlo simulation for it. And the argument value of ordinaries means you're going to use a regular old non-parametric Bootstrap. So later in this Bootstrap section, when we do the parametric, we will actually have a argument for parametric. I don't know why they just didn't call it non-parametric instead of ordinary, but that's what the authors used. Okay, now I'm going to put the results then into boot.res, and what's returned is actually a list. Okay, so let's take a look at this calc.t function. What boot does is it passes at least 2 sets of information into your function that you specify with the statistic argument. And ordering does matter. The first argument that's always passed is the actual data that was in the data argument for boot. You don't have to use the word data, but it seems to make sense to use the word data because it's my data. So that's why I use the word data there. That's always the first argument that R passes into this function. The second argument corresponds to your indices. Meaning, if you remember from last time, I showed you one way to take a resample was to resample indices. So this was on the bottom of page 22. So on this page last time I said, well, we could say sample, and then I'm sampling from 1 to 12, the integers. And these represent my indices for my y's, essentially, for what I want to appear in my sample. I say replacement equal true. And then to actually get my resample itself, I take my y vector, my original data, and then in brackets I put my, oops, let's just move that out of the way, I put in my index star, index dot star. Is everyone comfortable with that? Any questions? Okay. So at that time when I introduced that to you, I said, well, you know, this is actually how the boot function works. So as a second argument, the boot function always passes in then a vector of indices to use so that you can obtain the resample or resamples. I use the letter I. I could have used a different word there or letter. It just makes sense to do that. So that then, one resample at a time, the boot function, it's almost like using the apply function essentially. But the boot function passes in your original data and a resample set of indices for one resample into the calc.t function. And so typically the very first line of your calc.t function will be something like this. You find your resample. So my original data is going to be in data, and then I use bracket I and bracket, put the results into some object. I decided to call it D for the lack of a better name, and that is going to be my resample.
Those are the Y stars.
These will be my Y stars, yes. Then, once I have my resample, then I can calculate my statistic of interest. In this case, remember, it was just simply the sample mean. So let's actually try this out, because it's always good to make sure that this works before you actually even use the boot function. So I'm going to run my calc.t, and then let me actually move this over. It's right there. And then what I'm going to do is use calc.t with my original data, and for the indices, well, 1 to 12. So what should happen is I should just get my sample mean back that I had before, and indeed I do. I get 108. Okay. Let's actually look at what would happen for the actual resample. So I'm going to set a seed, so I can reproduce my results. My data is again in Y, and then I'm going to sample with replacement a set of indices. So just to show you, here are my indices. So Y8 is going to be my first observation in my resample. Y3 is going to be my second observation. So in other words, Y1 star is equal to Y8. Y2 star is equal to Y3. Do note that in my code here, I use an argument that I hadn't shown you before with the sample function, the size equal 12. It's actually the default. You know, whatever the length of this thing that's in X is, that's essentially how many samples are being taken. And for some reason, I decided to also include it. So if I go ahead and do this calculation here, so for this resample, I get T star to be 144. Okay, so let's go ahead and do 4,999 resamples. And so I'm now going to run the boot function, print off the results from boot.res, and this is what I get. Notice how quick it is. So this is just the default printing method associated with objects from the boot function. So first of all, you see the original, it's under the original column. This is what my statistic value is with the original data. So actually the boot function used the calc.t function 5,000 times. So this extra time is from the original data. And so since this is my first statistic that I'm calculating, R labels it as T1 and then a star. So T itself is 108. And then you also have two other columns. You have a bootstrap estimate of the bias of your statistic of interest. We'll look at that more shortly, exactly what that is. Also, I have a standard error. In other words, this is the square root of the estimated variance of your statistic T as estimated by the bootstrap. Okay, so let's explore more what's inside this boot.res function. So now this is a nice little application of stuff that we talked about in the R background check at the beginning of the semester. Meaning whenever you have, let's say, an unfamiliar function that you haven't maybe used before, and you get the results, you put in an object, one of the first things you should do is use names with it. Names boot.res. Since this is a list, we actually get a listing then of all the objects that are actually residing inside of boot.res. So for example, boot.res $T0 is my observed value of T. If I do a head on boot.res $T, I get a matrix that contains all my T stars. So this is a 4,999 by 1 matrix. And some of the other stuff that you see in there is kind of self-explanatory. Like statistic, that gives me my calc.t function. Yeah.
I have a question.
Sure.
If you use the boot function, how many resample you reduce? reproduct?
Well, when I use my boot function here, notice what I got, what I used.
Okay, but in your note you says this process is repeated r+1 times.
Yes.
So you mean the resample will repeat it r+1?
Well, this corresponds to what I said about 2 minutes ago, and that was calc.t is used 4,999 times for the resamples. And then the extra time is for the original data, r+1. Okay? So that's when I said calc.t is used 5,000 times. Okay? Also, based upon what we learned about in our background check, one of the first things you should do is run the class function with boot.res, so that you learn, okay, the class of an object coming from the boot function happens to be boot. And if I want to see the method functions associated with a class of boot, then I just say methods class equal boot. So there's not a whole lot there. We've actually run one already without me saying anything about it. Which one have we run?
Print.
The print one, yeah. Because if you remember, hopefully, I don't think I mentioned it, but hopefully in your other classes you've learned this before. If I just put an object, just type an object like this, what this basically means to R is run print dot whatever the class name is, and that's the function that's run. If I wanted to see print.boot, see the actual code for it, how would I do that?
Use the get anywhere function.
That's right. So I say get anywhere, since this is an invisible function, or non-visible function. And there we go. So if you want to know more about how the calculations are actually being done and in terms of what's being presented to you, look at the function. Let's see here. So another method function is the plot function. So if I do plot boot.res, so I use boot.res meaning boot results, bootstrap results. I just often use that by default. And so what the plot function does, with the plot .boot method function does, it gives you plots. So we have on the left a histogram. The dash vertical line corresponds to the observed value of t. And on the right, we have a QQ plot, not drawn exactly the way that I've done a QQ plot earlier in this class, but somewhat similarly. And you can still interpret it in a similar manner. So this is a normal base QQ plot. That's the default. You can actually get a chi-square with using a particular option with boot, print.boot. And so remember that we're interested in the sample mean. And we know for a large sample, the sample mean has what kind of distribution approximately? Normal. Okay. I have a sample size of 12 though here, and I have a right skewed distribution because it's exponential. What do you think about the central limit theorem here? Doesn't look like that n's large enough. Yeah. So this is a good, again, a good illustration. I think we've discussed this before, how the Bootstrap can allow you to evaluate some of your assumptions in terms of maybe the usual kinds of statistical methods that you might use in these kinds of situations, such as appealing to the central limit theorem. Okay, so that takes us to page 28. Well, let's say that you actually wanted to look at a particular resample. There's two reasons why you would want to do this. One would be to demonstrate in a classroom situation what the actual resample was. But a second reason is if, let's say, you have some unusual results occurring and you want to look at the actual resample that gave you those unusual results so you can figure out why did this happen. And the way that you can look at an actual resample is to use what's called a boot.array function, where the first argument, boot.out, that's where you can specify your results from the boot function. And then for the argument indices, that corresponds to I have true here, meaning I want the actual indices of the y's that were included in my resample. So if I put the results into save.end and then print off the first 6, we have the following. A matrix, a 4,999 by 12 matrix. The first row corresponds to the first resample. So this 8 that I have highlighted there, that means y1 star is equal to y sub 8. So the very first thing that was chosen in my resampling was y sub 8. And then it was put back in to, you could say, the pot of all your y's. The next one, y2 star, was y11. y3 star also happened to be y11 as well. Now there's another useful version of using the boot.array function, which actually will pop up in the next assignment, is if you put indices equal false there, and what you get then is some information that helps you relate the bootstrap to sampling from a multinomial distribution. So in my first resample, I observed y1 0 times. I observed y2 3 times. I observed y3 once. Note that this is not in the notes. But this will be helpful in the assignment. So what we can see here, that basically that first row, that matrix, is a vector of multinomial counts. Any questions? Okay, let's keep on moving on page 28. Well, let's actually do some confidence interval calculations. Now, if I wanted to, I could just simply, with the quantile function, take, let's see now, boot.res $t, type equal 1, and then probs equal, let's say the 0.025, and 0.95 quantiles from my all my t stars. And this would be what I would use to help find my lower bound and my upper bound for my confidence interval using the basic bootstrap method. Let's actually just, I'm going to go back to my notes real quick just to make sure you remember the, oops, wrong class, wrong document. Let me go back in my notes just to show you again what the basic bootstrap confidence interval looks like. Eventually. There we go. So then the bottom screen here, you can see what the basic bootstrap confidence interval looks like. So for the lower bound, I take 2 times t minus then the upper quantile from that t star distribution. So that's what I could do based upon, simply what I've done here in terms of I would take 2t times the 192. Or 2t minus, is that right? Yeah, 2 times t minus the 192, okay? There's actually a simpler way to do these calculations. There's a function R called boot.ci. So if I take boot.ci, for the first argument boot.out, specify boot.res, specify my confidence level with the conf argument, and then the type of bootstrap confidence interval that I want, let's say basic. If I run that, here's my basic bootstrap confidence interval. 23.2 to 169.6. You do need to be careful using that boot.ci function when you do some other intervals, and you'll see what I mean. Maybe not today, but definitely on Thursday. So it's nice that we have that available to us. Top of page 29 then, we can do some comparisons of this interval to what you would have probably done before taking this class, in terms of you would have calculated the standard regular old t distribution base interval for the mean. And we can see that the lower bound is 21.5, so it matches kind of what basic is doing. But the upper bound is quite different as well. Now remember, the underlying assumption for this t distribution base interval is you have normality for the y's, especially that's important when you have smaller sample sizes. Although the t distribution base interval is quite robust. But still, based upon what I saw on that QQ plot, I might be concerned about using the regular old t distribution base interval. Are there any questions? Okay. Now, unfortunately, the basic bootstrap interval is not necessarily one of the best intervals out there. It's a good place to start because you can see how the plug-in principle works with it in its derivation. Again, that might be a good test question. And the reason why the basic bootstrap interval doesn't work well sometimes is because it's not necessarily taking into account the variance of t, or you can say equivalent t minus theta. What I mean by that is that you see many situations in your past courses where the variance of your statistic is dependent upon a parameter. Whenever that occurs, what do you often do? Well, you replace the parameter with an estimate. Think of a walled base interval. The problem, though, with doing that is now you're inducing some additional variability in your confidence interval expression, and because of that, your confidence interval is probably not going to perform as well as you would like in some situations, especially for lower sample sizes. Just think in terms of a walled interval. Especially if you had my SET 875 class, you remember the walled interval for pi, the probability of success. The problem with that is that the variance for pi hat, the estimated proportion, is pi times 1 minus pi over n. Well, if you're going to use that for a confidence interval, you have to replace pi with pi hat. And that additional variability then is what's causing that interval some issues. So because of that, the basic bootstrap interval has some issues. So it can perform not as well as you would like. There is somewhat of a solution to it, and that is, suppose you know the existence of some transformation of t. So let's say I have a function h, and when I apply it to t, it's actually what's called a variance stabilizing transformation. What that basically means is that now the variance of h of t is equal to a constant. That parameter is no longer, there's no parameters anymore in the actual variance itself. If you can find a variance stabilizing transformation, h of t, and you can use that then with the basic interval in much the same way as maybe what you've done in other classes of finding a confidence interval. So for example, again, if you have my 875 class, you know that when we were working with an odds ratio, OR, we actually find a confidence interval for the log of OR first. Sorry, I'm running out of room. And then what we do is we use basically the inverse transformation back. Oops, that should be a log in there. Then we use the inverse transformation back to get back to the OR scale. If you hadn't had me for 875, of course, well, you should have took my course, but it's not a big deal. I would assume that you've probably seen in other courses where you use a transformation with a statistic, because that statistic is maybe better approximated with a normal distribution after that transformation. You still want then the interval based upon the original scale before the transformation, so you just use the inverse transformation. That's probably a longer explanation than what was needed, but this is how it works within the basic interval, is that you actually find an interval first for h of theta. So this is my interval for h of theta. And then to get back to the theta scale again, use the inverse transformation with it. So the h function itself could be the log function, then h inverse could be the exponential function. Now, how do you know what h is? Well, this is one of the things I cut out of my notes in comparison to when I teach a whole semester on the bootstrap. You'll see why I did that in a little bit. But what you could do is actually use the bootstrap, section 3.9 of Davison-Hinckley's book and my corresponding notes, talk about how you can use the bootstrap to estimate what this transformation should be. It's actually a very cool procedure to use. And I have a feeling you don't do this in Stat 980, but in maybe other courses like Stat 980, there's actually ways that you can derive an asymptotic variance stabilizing transformation. If you want to know how to do that, see Chapter 2 of my notes for Stat 950. Now, the reason why I chose to skip that material is because there are ways then, or there are confidence interval, there are bootstrap confidence interval procedures out there that are better than the basic interval and don't require you to do this kind of a transformation. The studentize and the BCA. In particular, the BCA is kind of cool where you actually make the assumption that one of these transformations exists, but you never have to specify it, and it all works out. You'll see as we go along. Okay, so should you use the basic bootstrap confidence interval in practice? Typically not, but we need someplace to start. Because a lot of the ideas in that help you see what the bootstrap is doing and also lead to better bootstrap confidence intervals. Okay, so what else can you do with the bootstrap? Well, let me back up a second. Probably the number one thing that people do with the bootstrap is confidence intervals. Because it gives almost an automated method to specify a confidence interval for a parameter from just taking resamples, and there's really no derivations that need to be done when you're just applying the result. There are two other things that the bootstrap's often used for: bias estimation and variance estimation. Bias not as much as variance, but it is used at times. And so I like to understand the bias of a statistic, for obvious purposes, because if you know that your statistic is biased, you might not want to use it. So back in Stat 883, you'll learn what the bias is. Expected value of t, your statistic of interest, minus the parameter, theta, that you're trying to estimate. We're going to call the bias beta, for the lack of a better letter. Now, we can write this a little bit more formally than what you would do in Stat 883. I could specify that my samples are taken with respect to f. So y1 through yn distributed f. Also, I can write my theta in terms of a statistical function that we talked about last time. That just basically emphasizes that there's essentially a mathematical algorithm that's being used to calculate this parameter of interest. So for example, when we're dealing with the population mean as the parameter of interest, simply it's the integral of, let's say, y f of y dy. Then the bootstrap estimate of the bias comes from this plug-in principle again, where you see an f, you put an f hat. Okay? We know what f hat is. It's our sample. It comes from our sample. It's our EDF. So that means I can essentially calculate the expected value of t given f hat. Usually, we will use Monte Carlo simulation to make that calculation. So, this is what we have. Just the average of the t stars for all capital R resamples. This t of f hat here basically says, okay, now use your sample with this mathematical algorithm that you have to calculate what you were doing before with the parameter. And we showed a very simple example with the sample mean. When we had the population mean versus the sample mean for the statistical function. And so what this ends up meaning then is that T of f hat is your original statistic of interest T. So what we would actually calculate then in practice for the estimate of the bias is the average of your T stars minus T. And that tells you information about is your statistic biased or not. Where could this be of interest? Well, for example, when you do maximum likelihood estimates, or maximum likelihood estimators, are they biased or unbiased? Or fixed sample size? Biased or unbiased? 50-50 chance. They are biased. Okay? They are asymptotically unbiased, but they are biased. So, for example, let's say that your distribution for your underlying data is normal. Okay? And you want to estimate sigma squared. What's the maximum likelihood estimate? Now I'll just give it to you. Does that look familiar? Instead 883? Okay, that's a bias estimate. But what happens as n goes to infinity? It's asymptotically unbiased. That whether you have 1 over n minus 1 or 1 over n, big deal. N's going to infinity. Okay. So then, what you might want to do then is calculate the bias of a statistic. And this is what you can do with it. It's kind of cool. You can use then this estimated bias to help you figure out a better estimate or better estimate for your parameter of interest. Yes?
I have a question about what the little b thing is. Is that the exact same thing as what was on the bottom of the previous page?
No.
Capital B?
No, because basically this is a Monte Carlo simulation estimate of
Right.
that expected value.
Right.
So that's why they're not the same.
So that what you circled, 1 over r, the sigma is t star r. Is that e of t given f hat?
Let's back up. Okay.
So I know you pointed an arrow to it. So you're subtracting the little t from.
Okay, so the question is this equal to this, right?
The entire thing or just that one part? That's the question.
I guess I'm not necessarily seeing your point. So I'll do some nice coloring here. That's what the blue things are equal.
Okay, that's
Okay.
Okay.
The yellow things are not equal.
Okay, that was my.
But they're
So it's
close. The-
estimated
the best
value, right?
Yeah.
The best
The bottom quantity is estimating this quantity. So what this is representing is the following. If you somehow, and this is actually kind of corresponds to problem number 1 of the assignment, if you could somehow list out every single possible resample, calculate T for it, calculate, since we're doing expected value T, calculate the average across all those possible resamples, that's what the expected value T given F hat would be.
Okay.
Okay.
That's what I thought it was. I was just clarifying.
Yep. Thank you. Okay, so again now the bias, the true bias, is expected value of T minus theta. How about we rewrite this expression so that only theta is on the left-hand side? And expected value T minus the bias is on the right-hand side. So that kind of makes you think now, if I know an estimate of beta there, maybe I could use that with just the statistic itself to come up with a better statistic to use to estimate my parameter. So what you could do is a bootstrap bias adjusted estimator is simply T minus B. So whenever you are concerned about bias, instead of just, let's say, using T as your statistic, use T minus B. There's actually a really cool example. Maybe we will get to it. I have a feeling we won't. That's just something I'll have to cut in comparison to what I said 950. There's a really cool example with this guy right here, where if you let t essentially be that statistic that I have circled there, and you apply a bootstrap estimate, you can see you are doing better. You can actually drive it all by hand without actually physically taking resamples. And then, in fact, do you think that this is a perfect estimator of beta? It's not perfect. So you might be thinking, maybe I could calculate the bias, calculate a bootstrap estimate of the bias of the bias. Bootstrap, I think I said that right. The bootstrap estimate of the bias. No, I did not. Basically, you want to know what the bias of the bias is. And so that then allows you to, let's say, do it like a second layer resampling. I think I mentioned this term the other day. Do a double bootstrap. And in fact, you could do a triple bootstrap. Do the bias of the bias of the bias. And you keep on going, and you can derive all this by hand, since that's such a simple expression up there, and show that, as you keep on going, you're improving every single time in terms of how good your estimator will be. If you ever pick up a copy of Davis and Hinckley's book, it's in chapter 3. It's also in my chapter 3 notes. But I decided to keep it a lot simpler, despite me talking about it a little bit. And there's your bootstrap adjusted estimator, or estimates. Okay, so let's talk about variance estimation. Of all the uses of the bootstrap, this is one of the big ones out there. Well, let's go back to what you learned in STET 883. So if I want to know what the variance of y is, let's just call the variance of y sigma squared. If I want to estimate it, of course, I can use the unbiased estimator of it. S squared, we often call it that, where we do have the n minus 1 in the denominator. One can actually prove, it doesn't matter what the distribution of y is, that this is actually an unbiased estimator. Okay? So that's for y. Y is a random variable. Well, let's now think of it in terms of t, our statistic of interest. Of course, a statistic is a random variable too. So it makes sense then that if I wanted to estimate the variance of t, all I would need to do is somehow observe a whole bunch of t's and calculate the same kind of variance expression, right? Now, in a real-life application, do you ever actually go out, take a sample, calculate the statistic, go out and take another sample, calculate the statistic, go out and take another sample, calculate the statistic? Well, no. You only take one sample, and you get to one value of t. So could we actually use this equation there to calculate the variance of t? No. But that's where then the bootstrap comes in. What we can do essentially is simulate that process. So the bootstrap estimate of the variance then is basically what you see at the top of page 32, except for you put stars on the corresponding quantities. I'm going to denote that as V sub boot, for the lack of a better symbol. V boot. Now this isn't exactly equal to that what will be the plug-in estimate of the variance. So if I were to do the plug-in estimate, so I wrote out my variance of t, and I put an f hat in there. Well, what is the variance of a random variable? Well, it's the expected value of the random variable squared minus expected value of the random variable, that quantity squared. And so that's what I did here. And notice how I have hats in there. So let's now come up with what would be then the Monte Carlo simulation estimate of these expected values. So here we go there. Put that right down there. If you do the math, look what happens. You have a 1 over r there instead of r minus 1. So the bootstrap, what the bootstrap actually tells you exactly what to do if you're totally relying on that plug-in estimator, is to use essentially a biased estimate of the variance. Well, we know better. Let's use the unbiased. So let's just stick a r minus 1 in there instead. And that's what we do. Do you think it's really going to matter if you have r or r minus 1 there? No, because of course you're always going to take a large R anyway. So that's why, it's really not a big deal. But you will only typically only see people use the unbiased version as the bootstrap variance estimator. A quick note. Earlier in the history of the bootstrap, people said, okay, you can get away with taking maybe just a R of a few hundred to do this bootstrap estimate of the variance, which actually could be helpful at times because often you have to calculate these bootstrap estimate of variances actually as part of a double bootstrap. And this includes Davison and Hinckley in their book. However, shortly after Davison and Hinckley's book was published, Booth and Sarkar in an American Statistician paper showed that indeed you do need to have a larger number of resamples to get a good value for B boot. So I would recommend at least 1,000 for R. And nowadays, unless you got a very complicated statistic, that's not going to be too difficult to do. Okay, so that's the variance. That's how you can use the bootstrap to estimate a variance. There's something closely related that I want to talk about to variance estimation. That is, use something called a jackknife. Just out of curiosity, how many of you have seen a jackknife in another class before? Everyone in my 873 class should be raising their hand because we actually talk about the jackknife with respect to estimating the correct classification percentages, let's say, for some kind of prediction method. And so the jackknife is, again, one of those few, I guess, names out there in statistics that is actually interesting. We have the bootstrap, we have the jackknife. And guess what? Tukey, who named the bootstrap, Tukey was actually closely involved in the development of the jackknife. He wasn't the actual one who first developed it. It was someone prior to him in the late 1940s. I don't remember that person's name, though. So the jackknife is very closely related to the bootstrap. And in fact, some people will just say it's just a special case of the bootstrap. So with the bootstrap, what we did was we took resamples from all the observations with replacement. Instead, what the jackknife does, it takes resamples of size n-1 without replacement. So you're still essentially doing resamples, but you're doing it without replacement, and it's a size of n-1. So how many possible resamples are there for the jackknife? N. So because of that, then people usually take all n resamples possible. Unless, obviously, if your n is just really, really, really huge. But typically, people will take all n resamples with the jackknife. There are 3 different versions of an expression for the variance estimator based upon the jackknife that I have seen. They're all very, very similar, but there are small differences to them. The first one I'm going to present is the one that we will use in this class. It's what was given in Davison and Hinckley's book. It's called, I'm going to call it VJack to help differentiate it from VBoot. And this is what it looks like. So n-1 squared divided by n squared. And then for your statistic of interest, you sum over all your observations. You take your observed value of your statistic and you subtract off your statistic again, but that subscript minus I notation says remove the ith observation from the data set and then calculate your statistic. So t minus t sub minus I, that quantity squared. Add them all up. Okay, well, where does this expression come from for variance that's calculated from the jackknife? Well, this is again one of these places where I felt as though I need to cut in terms of the explanation of where it comes from, that when I would do it in my Stat 950 class, we would actually spend about 2 days on this and some closely related stuff that corresponds to what's called the non-parametric delta method. So obviously you've seen the delta method before. There's actually something very closely related called the non-parametric delta method. And as I say here, without going into all the details, so I'm hand-waving here, I'm going to give you a brief explanation of where this comes about. Okay. So we talked about statistical functions before, earlier today, and I first introduced them last time. And a statistical function can be approximated using what's like a first-order Taylor series approximation. Okay, you've all done first-order Taylor series expansions before. It's a way to approximate some kind of mathematical function. If you think of a statistical function as a mathematical function, it kind of makes sense that there would be a way that you could approximate it. And the reason why you often want to approximate stuff is because what you get is often something easier to work with. And if you know from a first order Taylor series expansion, you're basically doing a linear approximation. And so the non-parametric delta method comes about by using a first order essentially approximation to a statistical function. And it leads to, without making any kind of distributional assumptions at all, it leads to the following expression as a general way to calculate the variance of any statistic at all. I'm going to denote it V sub L, where the L means linear approximation. 1 over n squared times the sum I equal 1 to n of these, what kind of look like almost script L's, squared, where you calculate one of those script L's for every observation in your data set. Okay, well, those L's are actually what are called empirical influence values. For every observation, you can calculate one. And where empirical influence values show up is in the area of non-parametric statistics, and specifically studying what's called robust statistics. And what they basically represent is a way to understand the influence an outlier has on a statistic. So, for example, if you're using the mean or the median, you would expect, an outlier to have more of an effect on the mean than it would the median. And this is basically can be represented in a numerical form by calculating these empirical influence values. Again, in my Stat 950 class, we would spend about 2 days talking about this and deriving these empirical influence values. Instead, what we're going to do is we're doing a shortcut here, which I think is perfectly fine to do. And that is, we can actually estimate these empirical influence values with the jackknife. So L sub jack is n minus 1 times t minus then the statistic t without the ith observation. Now let's appeal to some intuitiveness for why this would be a measure of influence. T with the subscript minus I says, okay, let's remove that ith observation from the data set, calculate my statistic of interest T. And if I compare it to what T is with all the observations in my data set, it kind of makes sense that if a statistic is very, can be influenced a lot by outliers, what's going to happen to the absolute value of T minus that T sub negative I? What would happen to it? It's going to be large, right? Is everyone clear on that? So then we can weight then that statistic then by n minus 1. How many observations essentially are going to the jackknife portion of it? And so this is a jackknife estimate of essentially the influence a particular observation has on the statistic. So once we have that then, we can take that, put it in there, and that's how we get VJack. And again, the really cool thing about it is that I'm making no assumptions about my data at all, other than, I guess, a random sample. And this is an estimate of my variance, all based upon using a first order Taylor series expansion, essentially. There's even other estimators that you can come up with based upon a second order, and you would expect them to be better as well. And yeah. If you take a whole semester of a PhD level non-parametrics course, you would talk about this kind of stuff. Okay, so there's actually even, and I just think it's kind of interesting, there's actually other ways to estimate these empirical influence values other than from the Jackknife. In fact, there's a really cool bootstrap way to do it. If you want to know more about it, take a look at Davison Hinckley's book in my chapter 2 notes. Okay, so that's what we're going to use for VJAC. Now, I do want to mention that there are two other ways that you will often see people use the Jackknife to estimate a variance. Let's actually, I guess we can talk about it in order. So what I call VJAC1, this I'm not going to use these at all in our course, but I do want to point them out. And in front of the summation, you have n minus 1 over n. And then in the summation here, we have t sub negative I minus t jack bar, which is just simply the average of all the t sub negative i's. And if you just look at that, intuitively you can kind of think, yeah, it'll probably be something similar to what we just were calculating before. And it is. That's presented in Efron Tibshirani's book. Another estimator that's typically used, I call it VJAC2, is exactly what VJAC is, except for we have just n minus 1 over n in there instead. Now, these two ways of doing the Jackknife estimate of the variance are actually more prevalent than the one that I showed you with VJAC. That's one of the reasons why I want to emphasize it. But a key is that as n gets big, is there really going to be any difference? Nothing practical, no. And also, in Efron Tibshirani's bootstrap book, which again was the first bootstrap book that really talked about the practicality of it, in their book, they even talk about some of these they talk about these different formulas, and they say that some of these other formulas that you see here on page 35, they're chosen based upon it as somewhat an arbitrary convention in terms of some of the terms in it, terms like the ends and stuff. And they do actually, on page 301 or so in their book, they do talk about the one that we're going to focus on. I guess one other small little story about this. So I've actually used a Jackknife estimator of a variance once for a paper that was published in the Canadian Journal of Statistics. And the referee, and I used essentially what we saw for VJAC in the paper. And a referee said, why aren't you using this one? This is what everyone else uses. And so when I replied back to the referee, I said, well, I'm using something that's based upon the non-parametric delta method. And while I didn't get a response from the referee, I would assume he said, oh, okay, that makes sense because the paper was eventually accepted. So that's why, again, perhaps I'm overemphasizing it. That's why I want to mention these other ones are often more prevalently used. Okay, so let's look at some examples that show how to do these calculations. Hold on a second. Yeah, we'll do this example, then we'll talk about the assignment. Okay, so this was the AC data again. And just for emphasis, here's what I ran before with the boot function. Here was my bias that's automatically printed from the print.boot function. And I actually give you some code that shows how one could actually calculate it by taking out all the t stars from boot.res and also taking out the original value of t from boot.res 2. And I get exactly the same value as what's given in the output. Not too difficult. Note that there was just a little bit of a typo there. You can remove that R. I guess I just like R's so much, I decided to randomly put R's into my lecture notes. The bootstrap estimate of the variance, VBoot, very easy to calculate. Again, all my T stars would be in the first column of the $T component of boot.res. So just use the var function with it. There you go. If I were to use the SD function for standard deviation as well, guess what? I get exactly the same thing as you see in the standard error column of the boot.res output. Let's compare that to what you would normally use for a sample mean. Again, in another class, you learned that one can actually derive the variance of y bar, let's say, is sigma squared over n. How would I estimate it? Well, I put a hat on top of the var, and I just simply replace sigma squared with s squared. And if you were to do that, take the square root, I get 39.32. Compare that to what the bootstrap gives you. Just about the same. So that's cool. And lastly here, let's do the Jackknife estimate of the variance. Okay, well, there's a nice function R called EMP-INF for empirical influence that will allow you to estimate those empirical influence values using the Jackknife. And then var.linear then takes those empirical influence values or the estimates of them and allows you to calculate the estimated variance using the Jackknife. So this is another reason why I'm using my VJack formula, is because there are nice functions in R that exist that automatically essentially do the calculations for you. Excuse me. So I'm going to create an object called L.Jack, EMP-INF. I put in my data. I put in my statistic that's used to calculate I put in the function name that's used to calculate my statistic of interest. And then I say S-type. That stands for statistic type. There's different ways that you can write your calc.t function and use it with boot.res. I'm only going to focus on one in this course, and that is where we pass in those indices, if you remember that. So when I say S-type equal I, that says, okay, that's how I wrote my calc.t function, where I'm passing in indices from the boot.res. I'm sorry, from the boot function. And then the type of estimate for these empirical influence values, Jack for Jackknife. Then with the var.linear function, I use the argument capital L for empirical influence value equal L.Jack, and I get 1417.715, which, let's see now, with the bootstrap estimate of the variance was 1456. Very, very similar. So that's cool. So on your own, since we're running out of time and I want to talk about the assignment, think about how you would program in the Jackknife variance estimator without the MP function or var.linear. What would be maybe one function that you would want to use to do these calculations? So I need to do something for every single observation, right?
Array.
Excuse me?
The array.
Not the array. So you're not even, let's say, using the boot function at all. Excuse me? The for loop. Yeah. So loop over all your observations in your data set, calculate your statistic of interest without the ith observation in it. Save the results, do some other stuff, and there you go. It wouldn't be too difficult to do. Okay, so let's talk about then the assignment. So it's a similar format to as the last time. Probably be a little bit longer than the last one, but not too bad. Right now I'm anticipating that there will be 2 assignments corresponding to the bootstrap material, where the second assignment might not be solely about the bootstrap. So same format as before. You can work in pairs to do this. What else? So it's again due Friday, February 20th at noon. There's two problems. So the first problem, just the purpose of it is just that you really understand what the distribution is of, let's say, T star. And it kind of corresponds to some of the discussions that we had that Robert brought up earlier in this class period. And I don't know, I guess I'm not a big fan of just giving you some data without any context. So here's some context here for this very small data set. So getting young children ready for school in the morning can be very, 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 very difficult. I don't know why I didn't put a very there. And in particular, I'm in charge of getting my son Keegan ready every single morning. Although this morning I didn't actually get him ready because he was up at 5 a.m. And my wife fortunately got up with him and got him ready. Don't understand why people just don't want to sleep in all the time. I mean, my two children, they're up almost every day by 6. Anyway, I'm looking forward to the day that they can sleep in. Anyway, so let's say so the first time that I kept track of the time it took me to get him ready, from when I said, okay, it's time to get ready, and by the time I got his clothes on, got his teeth brushed, it took me 15 minutes. Next time took me 10 minutes, and so on. So using this data, the goal is to estimate the mean amount of time it takes to get Keegan ready in the morning. Okay, so that's the setup. Just to put a little bit of context with the data. I purposely chose a very small data set because it's going to be a lot easier to work with, because you are going to find the exact distribution of T star without let's say doing Monte Carlo simulation to take your resamples. So first of all, part A, how many non-unique resamples are possible? Now what I mean by that is that this is one possible resample that one could have. Here's another possible resample, but notice the observations are exactly the same. They're just ordered in a different way. So what I'm asking you here is, how many non-unique resamples are there? And this basically goes back to Stat 882. It should be actually simple. 882, probably chapter 1. It's basically a combinatorics problem. Oh, I'll give you a hint too. It's a little over 3,000. Part B. Part B. Provide a partial listing of all possible non-unique resamples and calculate T star for it. Now, I don't want to see all a little over 3,000 T stars, but or the actual resamples. But what I want you to see is I want you to start listing out. Let's say this is resample 1, this is resample 2, this is resample 3, and do it in a way so that I can see a pattern forming of how you're iterating out all possible resamples. Again, calculate T star for each of them. So let's say that the number of resamples possible is, we'll just use the capital letter A, okay, just to be general. What would be the probability of getting this resample? Think simple.
1 over 100.
1 over A. Okay. Probability of getting this resample? 1 over A. Okay. So now that you know that, now you have a way to form the actual probability distribution for T star without using Monte Carlo simulation at all. And what I want you to do then is calculate the probability T is greater than or equal to 18 minutes, given F hat. Another way that people often denote this, and I want to introduce this is talked about a little bit later in the notes, people will often use this notation instead. You have to get used to both when you're dealing with the bootstrap. typically always use this one to be more consistent, but outside of this class, you'll see people use both, and you need to be comfortable with both, so that's why I brought that up there. So the probability star of T star is greater than or equal to 18. Part D says do the same thing, except for now use a multinomial distribution to find your probabilities. Remember early in the introduction to the bootstrap, I said, well, taking resamples is kind of like working with a multinomial distribution. So you should be able to write out, I do want to actually see a multinomial, actually a few multinomial distributions will be needed. Write out the multinomial distributions to find that probability. These two answers should be exactly the same. It's just two different ways to view it. So in some theoretical calculations that one would want to do with the bootstrap in terms of research, people often then go to the multinomial format in order to derive stuff. Part E that says, okay, why don't we just take some resamples using the boot function? And as you might expect, your answer in E should be close to the answer in C and D. So you have a really good way of checking your answers here. And then lastly, part F, calculate the 90% basic bootstrap confidence interval for the mean time. Use the exact distribution of T star for your calculations. How could be a way then that you can kind of check your answer? Use the boot.ci function with your actual, the Monte Carlo simulation aspect of it. Excuse me. Okay, so that's problem number 1. Are there any questions? Okay, so we're running out of time here. I do want to mention, well, I think that can wait till Thursday. You're welcome to start problem number 2 as well before Thursday. We will kind of go through problem number 2 though, like we did here with problem number 1. Are there any questions? Okay, well, that's it for today.